Okay, so this is going to be a video on antiderivatives and indefinite integrals. So first I'm going to talk about the antiderivative of a function. So if you have an f of x and you wanted to look at what we call the antiderivative, then what you're looking at is some potential other function, which on the screen I have here written as capital F of x, such that your capital F of x will have a derivative which is equal to your original function of f of x, small f of x. So this is a definition which helps you kind of determine later on how to evaluate indefinite integrals. So you would find your antiderivative and you would go from there to come out with the answer to that. But let's look at a couple of examples here of a function and its antiderivative. So we have f of x equals x squared as our original function. So a potential antiderivative for that f of x is this capital F of x, which we have equal to 1/3 x to the third. Now, the reason why this works out as a potential antiderivative is because if you take the derivative of f of x, this big F of x, or capital F of x, then you'll get the 3 rolling off of that exponent. So it's 3/3, which is just 1. And then you'll subtract 1 from the exponent by the power rule to give you x squared as the answer for the derivative of capital F of x. And x squared is what our original function was. So we see that f prime, or capital F prime of x, is equal to x squared, which is equal to just small f of x. And so we have the case here that the function is related to the antiderivative by taking the derivative of the antiderivative to get the original function. Now, let's take a look at the potential for antiderivatives to have a couple of different results. So there can be multiple different antiderivatives for any given function f of x. So if you have, for example, our f of x equals 2x in this case, then both capital F of x equals x squared and capital G of x equals x squared plus 2 are potential antiderivatives. Now, why is that? Well, we can take a look at what the derivative of each of these capital F of x and capital G of x are to see that we'll have a result which is equal to our original function of f of x. So if you take the derivative of capital F of x, which is x squared, you'll get 2x. And if you take the derivative of capital G of x, which is x squared plus 2, you'll get the derivative being 2x out of that as well, since that extra 2 that we added on is just going to go to 0 if we take the derivative. So you actually end up with 2x for both of these answers, which is the original function of f of x that we were looking for. So both capital F of x and capital G of x are potential antiderivatives of our small f of x. Now let's look at the general antiderivative. And in general, if you were looking at potential antiderivatives, you could add a constant on to whatever other antiderivative you got for a function, and that constant and that function together would produce a new antiderivative for your original function. So in general, if you're looking at the potential results out of an indefinite integral, you're looking at the set of all possible antiderivative functions. And so these results that you're looking at when you're doing the indefinite integral, which has this notation here, and when you're doing it with respect to x, you have the differential dx that you use to denote that. And you come out with this antiderivative here, plus this constant of capital F of x equals, or capital F of x plus c equals that indefinite integral. And so you can change what your f of x would be by some constant, and it would still be a result, which would be a valid antiderivative. And so in general, we just use this C to denote the set of all possible functions from that. As I've already said, this bottom line here just states that all the answers would be the same up to a constant of C for your f of x there. All right. Here are some basic indefinite integrals. So anytime that you're trying to find the result from a function that looks like one of these, this will be what the result at the end would be. Or this is how you could kind of change it to make it something that's a little bit more manageable. So if you have the indefinite integral of x to the n dx, then that comes out as x to the n plus 1 over n plus 1, and then plus c at the end for that constant of integration. If you have the integral of e to the x dx, that's going to be equal to e to the x plus c. Nothing too strange there. You're just figuring out the antiderivative of e to the x, which since e to the x is its own derivative, the antiderivative is also e to the x. And then we have the plus c for constant of integration as well for that one. If you're doing the integral of 1 over x dx, then that's going to be equal to ln of x plus c. So taking the case where you're having the derivative of the natural log being 1 over x, and just working backwards from that, is finding that 1 over x, if you're taking the indefinite integral, is going to come out as a function ln of x, will be kind of how you can come to that conclusion. There's also the constant of integration again at the end of that. And one thing to note is that for this particular case, you can't integrate if x is equal to 0, because that would be an invalid entry into the function, or it doesn't have a value of the function at that point. It's undefined. So that's one of those cases where if you're doing an integral like this, maybe later on if you're looking at definite integrals, you wouldn't be able to evaluate at that point of 0. So that's one of those situations that you have to watch out for later on down the road. And then we have a couple of properties here that have to do with manipulating the indefinite integral into something that's a little bit more manageable. So you have the integral of some constant k times f of x dx, and that'll be equal to k times the integral of f of x dx. And the reason why we can pull k out is because if k is constant with regards to dx, then that means that we're able to say that it has no bearing on what the actual value of the function or the interior of the integral would be, if it was on the inside or if it was on the outside. So it'd be the same sort of either way, because it doesn't change the overall value of the function between any of the points that we're integrating over. For the next property, we have the fact that you can integrate f of x plus or minus g of x dx and get the same result as if you were integrating f of x dx separately of the integral of g of x dx. And so you can either add or subtract the individual integrals of each of those functions and get what you were looking for before of either their sum or difference of the functions being integrated. And so that's the end of this video. Hope it was informative on integrals. They're a fairly important function to be using later on, and you'll probably be dealing more with definite integrals in terms of calculations and results. So look forward to those in a couple of chapters. All right, see you in a bit.